Hi, my name is Sarah Davis, and I'm going to be helping you go through this problem. Get ready for the first exam. So, our problem for tonight is give the orbital overlap sp3, 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 sp2, s to s, that kind of overlap for the bonds indicated below. Then rank the bonds in order of increasing length. So, got a little chart for the increasing length whenever we get there at the end. Got our little answer right over here. And this is going to be the bonds that we're going through. So, A is here between a chloride and a carbon. D is over here between a carbon and a hydrogen. C is the double bond between the oxygen and the carbon. And B is the carbon-carbon bond. These are all of our lovely valence electrons, and just to note, I drew in all the little carbons all the way around, just to keep a mental note. So, to start off with, I started working on D, did a little close-up right here. You can see I highlighted all the little bonds in blue, and then I wrote out the electrons. And so, I'm gonna start. All right, so this is a carbon and hydrogen bond. Carbon has 4 bonds. Sorry, 4 valence electrons. It can make 4 bonds. It wants to complete that octet. So whenever it hybridizes, this lovely electron right here, sorry about that. Lovely electron right here donates to this open p2 orbital. And whenever it hybridizes, it turns into sp3. Okay, you get the S because whenever this moves and fills in a little lovely spot right here, get S and then 3p. Looks like that. So this is going to be sp3. And then our hydrogen right here, its octet is full once it makes that bond right there. So it doesn't want anything else from anyone. It doesn't have any p or any p bonds to make, no valence electrons around it. It is happy and content being bonded to that carbon. It's got a full octet. Not octet, sorry. Got a full valence shell. And so all it has is that S characteristic. So it is just an S bond. So D is an sp3 to an S bond. Now, let's look at B, because since we already talked about how carbon has those 4 bonds, which makes it sp3, kind of just doing the same thing over here. Just showing you how this carbon to this carbon right here, it's making bonds and it's attached to all of these other lovely, or it's making those 4 bonds just like the first carbon was over here. And then it's got, so we've got 4 bonds here, 4 bonds here, which will make both of these carbons the same as they were before. Lovely sp3. Their octets are full, content, happy, and they both have 4 bonds. 4 bonded carbon is sp3. Okay, so it gets a little bit different whenever we look at C. So we have a carbon which is double bonded to an oxygen. That double bond is special. Lots of other little things over here. Because it looks like the carbon looks like it has 4 little bonds right here, and you would think that it's sp3 since we had it before. But whenever we talk about hybridization, any double bond, you kind of imagine it as just one giant bond, but it has just 2 electrons in there. So since we think of it as just one bond, despite having 2 electrons in there, it makes this carbon actually only have 3 bonds. I know it's a little bit weird, but that means this one is going to be treated a little bit differently. It's actually going to be an sp2 instead of that sp3 like we had before, because it is only making 3 bonds. And it is sharing a lot more of this S sigma bond with this oxygen. And you would think that this oxygen, let's write its electron configuration out real quick. So got that lovely S2, it's full, content, happy. And now we have its, ooh, that's wrong, not SP, it's P2. I need to look at my notes really quick, I know what I wrote. Okay. Now, it is almost content, almost full, almost happy. Almost. So, let's say this one donates, erases, we have hybridizes, and then we get sp2 and P. I'm writing that weird, I apologize. So it hybridizes. And we get all this full, these 2, but then there's one left out. It's one little p value. Okay, so oxygen has 1 double bond and has these 2 on the outside, and the p bonds come from the valence electrons. They're little pi bonds, they stick out on the end, and it looks like it has 2 pi bonds over here. But when you write out the configuration, it doesn't have 2 bonds, it actually only has 1 p bond, because one of the p bonds that it should have had is actually half filled. Okay, doesn't have that second one like it should. So it only has 1 p bond, making it an sp2. So this carbon double bond in oxygen is actually an sp2, sp2. That is the orbital overlap that it has for that one right there. Last but certainly not least, we have the chloride, don't move, chloride, carbon, okay, draw on those valence electrons, and there's actually another hydrogen. Now, first, gonna think, okay, now first let's draw on our bonds. Carbon is 4 bonds. Because carbon has 4 bonds, it is going to be an sp3. Now there's no double bond, creating actually, combination bond. So it is just going to be an sp3. But chloride only has one bond. But chloride is a little bit different because where it is on the periodic table is a little bit lower than our others. But it's got all this open, the little valence electrons. But it still has the ability to bond to more things. But whenever you write out its configuration, since it's a little bit lower, it's a little bit different. It has more S characteristic than P because of that. Okay. So whenever it hybridizes, it looks something like this. Okay. So, carbon has 4 bonds. It is the sp3. Chloride, whenever it's written out, hybridizes and becomes sp3. So, this is an sp3, sp3. Overlap, orbital overlap. But our problem isn't done, although we have main majority of what's being asked. It is not done just yet because we still have to rank them in order of increasing length. So, we know that the more S characteristic it has a shorter, stronger bond. So we're going to be looking at something like S and then SP. S is going to be greater. It's just an S bond is going to have more of the S characteristic than SP. And SP is going to have more than SP2. And then SP2 is going to have more than SP3. Because imagine you're breaking apart a candy bar. You just have the whole candy bar, then it's just one solid candy bar. But if you break it in half and then you combine it with something else, it's only half of that first candy bar that you started with. Now you keep breaking it down to more pieces and you have smaller and smaller amounts of that first candy bar that you started with. So that's sort of what that's trying to get with the more of the S characteristic. It's stronger, it's shorter, it's more in abundance. But we also have to note that shells of increasing size makes the electron density decrease. And what this means is that the farther out, say this is my little atom, 2 little electrons, it's a nucleus, the closer that the electrons are in relation to the nucleus, the stronger, shorter bond. So if we have a atom, and this is its first little thing, and then this is its next little thing, 4. Wait, 1, 2, 3, 4. And then we start getting more, and we keep adding more and more electrons. It increases the size overall of the element. Now increasing the size, there's less of a connection. Imagine this keeps getting bigger and bigger. Something that has a very big shell isn't going to have a strong enough pull as something who is smaller. They're closer together. So, better way to show it, something really big in comparison to something that is really small. It's automatically going to have that shorter bond because it has less space to travel through, less space to get through. So when looking at that, and we look back at our original bonds, C being a carbon double bonded to an oxygen, D being a carbon hydrogen, A is a chloride carbon, and then B is a carbon. First we can start off with easily saying which one would be the shortest, because that S right here from the hydrogen easily puts us at the top. So D would go as the shortest because it has the closest S characteristic. And then we just keep going down the list, and we would hit C because we have the 2s, which are bigger than the 3s, have the larger S characteristic. And then we get to a little weird place because A and B both have the same orbital overlap. But remember what we said, the increasing shells, increasing size. The farther down you go the periodic table of elements, the bigger it gets. Chloride isn't in that, it's not in the same place that the oxygen is. Not oxygen, sorry. The carbon is. It's a little bit lower on the periodic table. So therefore, it's going to have an increase in size versus carbon, who's going to have that smaller size. So B is actually going to have a smaller bond length than A because it is just a carbon-carbon connection versus a chloride-carbon connection. So A is going to be the longest, and B is going to be right here kind of in the middle. All right? And that is how you solve our problem. The longest is A, B, C, D, shortest is D, going in that order. We have lovely bonds here. A is an sp3 to sp3, C is an sp2 to sp2, B is an sp3 to sp3, and D is an sp3 to S bond. Okay, thank you.